All right, back from break. So we had been looking at momentum, and we were specifically looking at momentum applied to collisions. And we had looked at some collisions that were inelastic, where objects ran into each other and stuck. But now we're looking at collisions that are elastic. And so that says that the kinetic energy would be conserved from before and after the collisions. And these are the equations that we came up with. Now, we looked at some examples. We've been looking at some examples. Here are billiard balls. We said in the case of two billiard balls running into each other, to a very good approximation, kinetic energy is conserved. It turns out that billiard balls are very rigid, and they transfer momentum very effectively. They're elastic during the collisions. And so we had gone in and shown what would happen for a couple of billiard balls running into each other. And now what we had come back with was an example where the masses were not the same. So if the masses are, I used A and B, look at that. So if the masses are not the same, then I have just one initial velocity, u. The masses are ma and mb. The velocity after, using these big complicated formulas. So you can see, one thing to see here is, see how the formulas they're all complicated. They depend on both initial velocities and all this different stuff in terms of the mass. But they simplify if, in this case, one of the objects is at rest. So if one of the objects is at rest, then the two formulas simplify to these two formulas here. And when they collide with each other, and object A comes out with velocity A and object B comes out with velocity B, we had solved this before. If MA is really, really big compared with MB, if the mass is really large compared with the mass of B, then object A hardly feels the effect. So to a good approximation, object A continues on with velocity u, and that's what this formula is telling us. If mb is really, really small, ma over ma, that's almost a ratio of 1, and so the object, the really high mass object, keeps moving. Now what happens if, if an object with a lot of mass runs into an object with not very much mass, and the collision is elastic? Well, in this case, I can ignore mb, but there's a factor of 2 here that tells me that this object will separate at 2 times u. Now, we could check to see if this is really elastic. One of the ways we said we could look to see if a collision is elastic is to look at the relative speed of approach and then look at the relative speed of separation. So, in this case, before the collision takes place, what's the relative speed? And the relative speed is u. U tells us the rate at which the two objects are closing on each other. And look, in the after collision case, the relative speeds continue to be u. So it's 2u versus just 1u. Now, the other case we looked at was where ma is really small. We said this is a very low mass object running into something with a lot of mass, like running into a brick wall. This is like a tennis ball running into a brick wall. If it's perfectly elastic, then the tennis ball reverses its direction and goes back with the same speed it came in with. The brick wall doesn't really move much, okay? Or the big heavy object. If I throw a tennis ball at an automobile, for example, in neutral, so put the car in neutral, the car still doesn't feel much of an effect from that, right? All right, and then the relative velocity here is also u. Okay, let's try, what about a nuclear collision? Doesn't sound like a good idea. So in this example, we're looking at a couple of nuclei. We're looking at a proton running into a helium nucleus. Now, these are not atoms. Well, we're not really thinking about the electrons here. So what we're doing is we're taking a beam of protons. Now protons by themselves are classified as being hydrogen, right? A proton by itself is a hydrogen nucleus. So we can think of this as a hydrogen running into a helium, but it's just the nuclei. The electrons are off doing something else. And so for this collision, what we can do is say that the helium is a target, I guess, is what they're saying. And here comes the proton. Now they're saying that the proton has a mass of 1.01 atomic mass units. And in this example, it's coming in pretty fast. So the proton beam has a bunch of protons in it, and they are moving 36,000 meters per second. So that's a good speed. Now they're going to run into a helium nucleus, and a helium nucleus has a mass of 4.00 atomic mass units. And no, these numbers are not coming off the periodic table. The periodic table averages masses over different isotopes. So there are different isotopes of helium. Some have a mass of 3, some have a mass of 4. So this is a specific isotope of helium. It's the one with 2 protons and 2 neutrons. The proton is just a proton. So what are the velocities of the proton and helium after the collision? And what we're assuming is that this collision is isolated, and that the 2 nuclei coming out looked identical to the 2 that went in. Now it's possible the proton replaced another proton, but we won't worry about that. All right, so let's take a look at this collision. And so here is, just for reference, the mass of a proton is 1.00. I wanted another couple sig figs. I wasn't really happy with the 1.01. So I went out to 1.0073 atomic mass units and then compared that to a neutron. A neutron is 1.0087 something 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 atomic mass units. An electron, which is not involved in this, is 0.00055. It's much less mass. Yeah, that's 0.00055. And then, yeah, we did get that right. And then the helium nucleus has a mass of 4.0015. So I just wanted to point out, you know, a few more sig figs so you can kind of get a feel for what these nuclear masses look like. All right, so the proton comes in. Now remember, it's bouncing off, it's elastic. It's bouncing off something heavier, and what our formulas have told us is that when something lower in mass hits something that's higher in mass, it bounces back. Its direction is going to reverse. Okay, so back to these formulas. If MB is larger than MA, the numerator is negative, and the lighter object will bounce back. If it's elastic, and the one of the objects is at rest, that's what's going to happen. So we can already take a look at this and say, here is the proton coming in. It's going to hit the nucleus, and then it's going to bounce back. Now, oh, these are forces. Okay, got it. So there's a force acting on the proton, and there's a force acting on the nucleus of the helium. And the proton doesn't necessarily touch the nucleus, right? They're both electrically charged. They're both positively charged. And since they're both positively charged, the force acting between them, it's electric. It's an electric force. There could also be some magnetic components of the force present, but it's an electric force of repulsion. So we're used to thinking of collisions as where things hit and there's a contact between them. But when you take a close look, you realize that these atoms and molecules, they're not billiard balls. They actually interact through electric and magnetic forces. And so what happens is, as the proton approaches, these two guys begin to repel each other. The helium nucleus experiences a force in that direction. The proton experiences a force here, and that slows them down and then they push away from each other. Okay, or this was already at rest, right? So this is at rest, this comes in, this begins to pick up speed, this slows down, and then reverses. Now momentum conservation still works. This is an electric collision. It's a force mediated by the electric force. So we can just plug numbers into the formulas then. So I plugged in the mass for the proton and the mass for the helium nucleus. Those are the two items that we're working with. And it said that the speed of the proton after the collision is going to be equal to 0.60 negative. 0.60 times the speed coming in. And I used V naught this time instead of U. So here is the proton coming in, approaching this. Here's the helium atom with the electrons in place, but the proton is just going to sail right past the electrons, and then it's going to get pushed away from the nucleus. So even though it's a bunch of helium atoms that we're looking at, we can ignore the effect of the electrons pretty much. All right, so the velocity here then is given by this expression. This is minus 0.60 times V naught. And that worked out to be minus 2.15 10 to the fourth. And for the helium nucleus, again, plugging the numbers in, the helium nucleus separates at 1.45 10 to the sixth. Now the speed of the relative speed of separation, if I add these two numbers together, the relative speed of separation is 3.6 10 to the fourth, which we said had to be the case for an elastic collision. So one more picture. Here is that helium nucleus. Here is the proton coming in at 36,000 meters per second. And then that's the relative speed, the 36,000. The proton bounces back, or gets pushed back by the electric repulsion at 21,500 meters per second. And the helium nucleus, as a result of that electric force, gets pushed forward and picks up to a speed of 14,500 meters per second. Okay, so the rate of separation matches the rate of approach. All right, now with inelastic collisions, we've been looking at all these elastic collisions. Some of the initial kinetic energy becomes thermal. So we don't have as much kinetic energy after the collision. The energy gets lost to thermal or possibly potential energy. Kinetic energy after can actually be bigger than initially if there's an explosion. So you can have an explosion where something is sitting at rest, it has no kinetic energy, but because of the release of chemical energy during the explosion, during whatever chemical reaction set that off, pieces are flying at really high speeds. And so you've got a lot of kinetic energy after the explosion, whereas you didn't have any kinetic energy before. So you can lose kinetic energy during a collision, or you can acquire even more kinetic energy during an explosion. Now the inelastic collisions are when the objects stick together and move away at the same speed. So here we are. Oh, it's the railroad cars. So it's the railroad cars again going, 55, 60 miles an hour, something like that, and they run into each other and they somehow survive the collision. Now, after the collision, what they're showing here is they're moving off together. So it looks like the very same example as before, except they're asking us about how much kinetic energy went thermal. How much of the kinetic energy went thermal during the collision? So let's go back and kind of review what happened here. The momentum conservation, if you remember, said that m1 v naught plus 0 is equal to m1 plus m2 times v. Now m1 and m2 were 10,000 kilometers, v naught was 24 meters per second. When we solve the momentum equation, it tells us that the two cars together are going to head off at 12 meters per second. So we've got the speeds before, we've got the speed after, and we know how much mass we have. in each one of the objects. So let's take a look at energy conservation, I guess is what we're going to call this. The kinetic energy initially, before the collision, is 1/2 m1 v naught squared. Putting all of those numbers in gives us 2.88 10 to the 6th joules, 2.88 million joules of kinetic energy. That's the kinetic energy of railroad car 1 coming into the collision. Now, railroad car 2 doesn't start out with any kinetic energy at all, so that's 0. Now let's look at after the collision. After the collision, what we've got is, well, the kinetic energy for these guys would be 1/2 m1 plus m2 times v squared. And the v that we want to use now is the 12 meters per second. So we used momentum conservation to find out what the speed would be after the collision, and now we can use that velocity to calculate the kinetic energy. And what we're finding is the kinetic energy after the collision is 1.44 megajoules. So it looks like, from the numbers, half of the kinetic energy is missing. So, and we know that whatever kinetic energy is missing, in this example, it must have gone to thermal energy in the collision. So if you check out the coupling mechanism on those railroad cars, they're going to be really warm. Now I guess there's another possibility here. It could be that one of these railroad cars, or both of them, have spring systems built into them, and so they come together and they store the energy in a spring, and then the mechanism locks so that the spring has been compressed, and then they travel off together, but there's a spring in here that's now compressed, that's been locked in place, and then at some point we can release that and the spring can push the two cars away from each other. Again, that would be a way to conserve mechanical energy. All right, so that was looking at the energy loss, the kinetic energy, the generation of thermal energy in the collision. All right, let's move on and look at collisions, a couple of examples in 2 dimensions. So in 2 dimensions, I'm going to have to conserve momentum in the x, and I'm going to have to conserve momentum in the y. They both have to be conserved in this example. So what's going to happen here? What's going to happen here is that we have an object coming in. We're going to treat this as a target. So let's just have one object moving and one object at rest for this 2-dimensional example. So here comes object 1. It comes in with a certain momentum. Instead of continuing along the x-axis, object 1 bounces off at some angle. And object 2 bounces off at some angle. Now, what has to happen in a situation like this, and let's take a look at this, is that the momentum in the x direction that the object A started out with has to be equal to the combined x momentum after the collision. In the y direction, the two momenta in the y, the momentum in the y for A, the momentum in the y for B, those have to be in opposite directions and equal amounts. So let's see how this would work. Here's the object M1 coming in at V0. Here is object M2 at rest. After the collision, M1 is heading off at θ1 and a speed of V1, while object 2 is directed at an angle of θ2 with a speed of V2. Now, in this example, they are telling us that it's 2 billiard balls, and so the masses are going to be the same. eventually. So what I wanted to do was write the equations down more generally at first, and then we can come back and take a look. So in the x direction, m1 times v naught, the momentum in the x direction here, has to be the combined momentum in the x direction of m1 and m2. So that would be m1 v1 cosine theta 1 plus m2 v2 cosine theta 2, and that's what I've written right here. So this is conserving, that is a statement of momentum conservation in the x direction. Now in the y direction, we start out with no momentum whatsoever, and so this is zero momentum in the y, but after the collision, each of the objects ends up with some momentum in the y direction. Well, how can we start out with zero and then end up with these two momenta in the y direction? And that will work as long as the momenta are equal and opposite. That will also give us a total momentum of 0. So that's kind of it. What we can do here is write this as m1 v1 sine theta 1 and m2 v2 sine theta 2, and then make sure we get the minus sign put in there to show that these are in opposite directions. So these are the two general statements about what has to happen in terms of momentum conservation. Now, what they told us in the problem is that m1 equals m2. Well, that simplifies things because now I can drop all of the masses. All of the masses drop out, and then what also happens here is that the two angles, if let's take the second equation here, if m1 and m2 both drop out. Let me take a look at the. Oh, they gave us both angles. Okay, so this is just given information. And what I've done is I've treated theta 1 and theta 2 as 45 degrees. I did not call this minus 45. Instead, I put the minus sign here. And so if the angles are the same and the masses are the same, then this equation will only work if V1 equals V2. So this is just all the given information. We need to move on to the next page. Okay, so in the x direction, what we're seeing is V0 is equal to V1 times the cosine of 45 plus V2 times the cosine of 45. In the y direction, V1 has to equal V2. And that's because the masses are the same, the angles are the same, and the momentum needs to match. So I can take the V1 and V2, I can substitute in V1 for that, and it says that V0 then is equal to 2 times V1 0.707, and if I solve for V1, V1 then is equal to 0.707 times V0. And so I've solved this, so V1 and V2 each are going to be 0.707 of the initial speed. The initial speed was 3.0 meters per second. If we go back to here, that's how fast they were going, and so those are the final speeds. So here are the final speeds that we ended up with for the two objects. Now the question comes up, I think I asked this question. Did they ask it? No, I added this on. That's good. Very good. So is this collision elastic? We never were told whether or not this was going to be elastic. Let's try it. The initial kinetic energy we have is 1/2 m v0 squared. The kinetic energy of object 1 after the collision is going to be given by 1/2 m v1 squared. Now we found out that v1 is equal to 0.707 times V0. That number right there is the square root of 2 over 2. And so if I plug that in and square it, I'm getting 1/2 times 1/2 m V0 squared. So 1/2 of the initial kinetic energy is in object 1. And when I look at the numbers for object 2, they're identical to object 1. So the energy splits. Half the energy goes with object 1, half the kinetic energy ends up in object 2. The collision is elastic. So now that was based on, they gave us a lot of information. So they gave us information of the 45-degree angles, and the masses were the same, and it does work out that the collision was elastic in this case. All right, so here's some recommendations about how to solve these momentum problems. Identify your system of objects. If it's complex, if things are complicated, change your major? I'm not sure. If things get complicated, identify subsystems where one or more conservation laws apply. Is there an external force? If there is the collision time short enough that you can ignore it? Draw diagrams. Diagrams are always good. And then select a good coordinate system to work in terms of. Apply momentum conservation. If the collision is elastic, also use kinetic energy conservation. Check units and check to see if your results make sense. All right, we're going to move on to a bit of a different topic now. We're going to start looking at a topic that's called center of mass. Now that may be something that that you've heard of, I'm guessing. So let's take a look at a couple of pictures. We have a diver here jumping off this diving board. This diver jumps off the board, and the diver maintains exactly kind of the same shape, the same relative rotation. So the diver just maintains verticality. So what we would say is that diver is an object that is not, it's not rotating. The diver is not rotating. What the diver is doing is called translation. So when I have an object, an extended object like this, and I can follow the center of mass of the object, and then relative to the center of mass location, the object's not rotating. There's no rotational energy here. Now, in the second dive, here is the other dive. The diver gets back out there and does a different dive. This time the diver actually goes into rotation. So this time there is both translational motion and there is rotational motion. Both of those take place with this second picture. So what we can do is we can take a look at what happened to the center of mass. In both dives, the center of mass followed a parabola. It followed our projectile motion back from chapter 3. So, and that's what happens with the center of mass for an object. Here's another example with a wrench. So here is a wrench that has been thrown across a table. Now the table is not illuminated, the wrench is, because it is a straight line here. So you can see where the center of mass is for the wrench. What we can do is we can draw one line that at every location goes right through that point on the wrench. And that tells us right at that location is where the center of mass is. All right, what are the formulas for identifying the center of mass? It's got to be something that sort of averages over the location of where the object is. And so if I have two objects, one has mass A, one has mass B, what I can do is I can set up a coordinate system. Now if there's just two objects, I can set up the coordinate system so they're both on the x-axis. Now what we could have done is we could have put the origin at one of these locations, but they chose not to do this. So what we can do is then measure from the origin out to object 1, that's a certain distance, and then measure from the origin out to object 2, that's a different distance, and then what we can do is say that there is a center of mass somewhere between the two objects. Now the location of the center of mass depends on how much mass each object has. And from the picture they drew, it looks like object A is heavier. So the center of mass is closer to object A than it is to object B. All right, so here is the formula for determining where that center of mass will be located. What we do is we take each one of the x values that tell us the position of the object and multiply that by the object's mass. So it becomes what we refer to as a weighted average. So if the two masses were the same, that weighted average would be halfway between the two objects. If MA and MB were the same, then I could get MA and MB to cancel with MA and MB on the bottom. This would become XA plus XB over 2, and it would say that the center of mass is located halfway between. But if one object is heavier, then the center of mass is shifted towards that heavier object. All right, so the formula ends up looking like this. Now, they're using big M to represent the total mass of everything in the system. I tend not to use that. I can't. I tend to prefer this so I can see all the MAs and MBs at all times. Okay, so here are 3 guys on a raft. So here are 3 people, roughly equal mass. They're all the same mass. They're on an inflatable banana boat sitting along the x-axis, and they're located 1 meter, 5 meters, and 6 meters, measured from the end of the inflatable. So where is the center of mass of those 3 people? We're going to ignore the mass of the boat. We're going to say the boat's mass, it's just a plastic inflatable, not much mass to it. So using the formula that we were given and extending that for 3 objects. Now these objects all have the same mass. So x1 is 1 meter, x2 was 5 meters, x3 was 6 meters. I'm going to add all those numbers together. I factored out the mass. Now don't get the mass of the individuals mixed up with the m, that is meters. So this is 1 meter, 5 meters, and 6 meters. And then, just following this formula. So I'm going to get 3 masses below. The masses will cancel out. So now it just becomes the average value of 1, 5, and 6. And so the center of mass for that works out to be 4 meters. Now, I did this. I don't know how useful this is. Since everything is right along the x-axis, the center of mass coordinate for the y direction is 0, and the center of mass coordinate for the z direction is also just 0. Okay, so that's an example of how these center of mass problems are going to work. What if we move on and do a 2-dimensional example? So in this case, I've got 3 masses, 1 here, and 1 here. Now they're not all lined up. So I can't place them all along one axis. I'm going to have to do 2 separate calculations. I am going to have to, here's where they're suggesting the center of mass might be. And they're saying that I'm going to have an x and a y component for the center of mass. Now this time I've got 3 objects. The masses are the same, again, this time 2.5 kilograms. They're located at the corners of a right triangle. The 2 sides are 2 and 1.5 meters as shown. So let's see if we can use the very same formula, but we'll use it twice. Now in the x center of mass, what I'm going to do is use the x-coordinates. The x-coordinates are 0, 2, and 2. So let's go back and take a look here. If I look at the objects, object A has an x-coordinate of 0, and that just drops out. The x-coordinate here is also 0, and then the x-coordinate for this object is at 2 meters. I'm sorry, this one's 2. at 2 and at 2. So x equals 0, x equals 2, x equals 2. And those are the numbers that I need to get the center of mass for the x direction. Now what about in the y direction? Well, in the y direction, the coordinates are 0, 0, and 1.5. So in the y direction, when we carry out the calculations, we're going to get a factor of, we're going to get a mass plus mass plus mass, which will cancel the masses here. I'm going to get a factor of 3. So it's 0 plus 2 divided by 3. That's 4 divided by 3 is 1.33 meters. And then in the y direction, it's 0 plus 1.5 divided by 3. That's going to give us 0.5. So those are the coordinates. And now that we have calculated that, we got to go back and identify where that is located. So 1.33 in the x direction would bring us about here. This would be 1 in the middle. And then in the y direction, 0.5, 1, 1.5. Yeah, that looks like they got that center of mass location. Looks fine. Looks just about right. All right, let's, I think we've got some time here. There's one last example. It's a fairly challenging example. I'm going to go ahead and go through it just to show you how we would carry out a calculation for the center of mass of a continuous object. So rather than individual objects and kind of adding together the effect from the individual objects, now we want to carry out an integration. So let's try that. Let's take a look at what we have is a thin rod, and we would guess if this is a uniform stick, the center of mass should be right in the middle. Is there a way we could go through and demonstrate that? Is there a way we could go through, do some calculations, and show that the center of mass is in the middle if it's uniform? And that's what they asked us in part A. But in part B, they say, let's go back and reconsider what would happen if the material gets denser as we move along the length. Right? So you've got some kind of an object. It's got a lower density at one end, and it's got a higher density at the other. Well, if the right side of this is higher density, that's going to take the center of mass and shift it to the right. And the question becomes, by how much? Well, it depends on how the density varies. What they're telling us in part B is that this density, they're using lambda to represent something called the linear mass density. That is, how much mass per length do we have? And we'll see how we handle that mathematically. Now, at the left end, I've got a certain density of lambda naught. At the right side, the density has doubled, and the density increases steadily from left to right. So here's the example. Let's say that this rod has a length, I'm going to call it A, and it has a total mass, I'm going to call that big M. And then here is a section of that rod. It has a length of dx, and it has a mass of dm. Now if I add all the dm's together, I get total m. If I add all the dx's together, I get total length. Now how are we going to define the linear mass density? So the linear mass density, lambda, can be written as dm dx. How many kilograms per meter at each location? So that density, there's a value for the density at each location along the length. Now this allows me to write dm as lambda times dx. So you go, well, how much mass is there in each little section? It depends on the density times how large the little section is. Now when we're integrating, like we are here, the formulas for the center of mass require us to take an integration of x times each individual piece. If you stop and think about it, this is kind of like the summation that we were doing before, but because it's an integration, it's a continual summation. So you know from your calculus classes that integrating is related to carrying out summations over values. So instead of summing together a bunch of individual pieces, we can add them together in a continuous fashion by carrying out the integration. Now the same thing with the mass itself. We can add together all of the mass pieces combined. So this is the formula, the integral formula for center of mass. What we can do now is take the dm and substitute lambda dx. So here is lambda dx. I split that up. The lambda is here, the dx is here, and the x ended up in the middle. Now remember, if in part A, lambda is a constant. And so if lambda is a constant, that's not a difficult calculation to carry out. Lambda would be given by the total mass divided by the total length. Now in the formula we have here, lambda just drops out. There's a factor of lambda on top, there's a factor of lambda below. They're constants, they come outside the integration sign, and they cancel out. So the only thing left in the integration now to calculate is x dx on top and dx below, and we're going to integrate from 0 to a. This becomes 1/2 x squared from 0 to a. The denominator becomes x evaluated from 0 to a. So that's 1/2 a squared over a, and it says that the center of mass is located for this uniform rod at 1/2, it's located right in the middle, 1/2 a. All right, now think about this one because this was the easy example, right? Now what we're going to do is we're going to move on and ask what happens if the density is not uniform. Now a lot of the stuff is going to stay the same, so let's go back actually. We can go back and say this still works, this still works, this all still works up to here. Where part B is going to diverge is here. Lambda is not going to be a constant. Lambda expression is going to be more complicated. So we can use this expression that we've set up, but we can't use the idea that lambda is constant. Instead, what we're going to have to do is this. Now, it told me that when x is equal to 0, lambda is equal to lambda naught. So I wrote that. Lambda equals lambda naught when x is equal to 0. And then when x is equal to a, lambda needs to be equal to 2 times lambda naught. So I wrote that as x over a times lambda naught. So here is my expression for how the density varies as a function of position. Okay, and that's one of those expressions you kind of have to stop and think about. Does it work? They said that the density increases linearly. This is a linear formula. It depends linearly on x. When x is equal to 0, the density is lambda naught. When x is equal to a, lambda is equal to lambda naught plus lambda naught, which is 2 lambda naughts. All right, there we go. So let's take this expression and plug that in to our formula, and what that worked out to be, this is lambda naught times 1 plus x over a, the denominator 2, lambda naught 1 plus x over a. The lambda naughts cancel out, but this extra factor, these extra factors don't. So those aren't going to factor out because I can't bring them outside the integration sign. I have to carry out the integration with the 1 plus x over a in place. And that gave us 1/2 x squared plus 1/3 x cubed over a divided by x plus 1/2 x squared over a. Each of these has to be evaluated at the endpoints. And when I carry out the integration, I'm getting 1/2 plus 1/3 on top times a squared, 1 plus 1/2 in the denominator. Here I have an extra factor of x in the formula, and here I don't. And that leads to a squared over a, which makes sense. The units make sense. They've got to have one factor of a. And then it's 5/6 divided by 3/2. 5/6 divided by 3/2 becomes 5/6 times 2/3. That becomes 5/9. So the center of mass location for this non-uniform rod is going to be at the 5/9 A position. Okay, so that was kind of interesting. I hope that was useful. You know, any kind of integrations that we do, we're going to keep those pretty simple. Again, the homework problems are probably a good representation of what could possibly show up on a midterm. But sometimes it's good to go in and take a more detailed look in the lectures at least, and see how some of these calculations work. Now, once we've determined the center of mass of an object, then we can go back and use that center of mass to follow an object that might be in rotation, for example. What point is it going to rotate around? Now, in this example, with this two-stage rocket, what we're saying is that there is a center of mass at launch, and the center of mass will continue to follow a path of projectile motion. So the center of mass continues to follow the path of center of projectile motion, even though the two stages separate right here. Now the two stages separate in a way where this one gets pushed back and it's not moving at all, and it just drops. And then another stage continues on. If we look at the path of stage 1 and stage 2, the center of mass of those two continues to follow the original path. When we have some kind of an explosion like this, the center of mass is unaffected by that. So that's interesting. Now, since these pieces both came off with no velocity in the y direction, that means they'll also fall together. And so I had added that in. Both the first stage and the second stage are going to be dropping in elevation together. They should hit the ground at the same time. Okay, and at the points where they hit, we can find the half. Well, are the masses the same? Yeah, they are. So the two stages have equal masses. So the center of mass point will be halfway between the two stages where they've landed. Okay, so that's it. A lot of stuff in the momentum chapter. I'm sympathetic. If this stuff seems a little tricky, it can be. So again, put some time into it. Whatever question you guys have, whatever questions, let me know. And stop by office hours and we'll get those looked at.